another property is this associative property, right, which says that the convolution between x and another function, which is equal to the convolution of h1 and h2, is equal to a function equal to the convolution of x and h1 and the convolution of h2. Right. So what this is saying is that when you want to compute the convolution of three functions, it does not matter if you perform the convolution first on these two functions or if you compute the convolution first on these two functions. Okay. So therefore, the following expression here is unambiguous because when you write this expression without putting in the brackets, there's no confusion because no matter how you compute, right, no matter in which order you compute the convolution, the result would be the same. Okay. Now, what are the system implications of this? Right. So if you look at this first figure here, right? So what you're doing is that you're first taking xn and passing it through, h1n to get wn, and wn is therefore the convolution between x and h1n. Right. Now yn is the convolution of wn and h2n, and wn is this thing above. So if you're looking at a convolution computed like this, you're effectively looking at a system where you take x and first pass it through a system with impulse response h1, followed by a system with impulse response h2. Okay. Now this associative property tells us that this is equivalent to passing xn through a system with impulse response that is equal to the convolution of h1 and h2. Okay, so this is saying that, if you have a system that is equal to the cascade of two subsystems, then the overall impulse response is just the convolution of these two subsystems. Okay. Now, by the commutative property, we know that the convolution between h1 and h2 can be written as the convolution between h2 and h1. Right. So this is by the commutative property. Okay. And then, right, by sort of splitting this into two subsystems, you get, the cascade of h2 and h1. So what this is saying is that when you have a system with a cascade of h1 followed by h2, it is equivalent to a system with a cascade of h2 and h1, right? So when you have cascade of multiple subsystems that are linear time invariant, then the order for which you pass the signal through does not affect the output. Okay. Right. So as I just mentioned, this is saying that the overall system response does not depend on the order of the systems that are in cascade. Right. But you should note that this is a property that is specific to linear time invariant systems. If you have systems that are nonlinear, then this would not hold. Okay, so not for nonlinear systems. right? So we can look at a simple example, right? So suppose you have this input xn that you first pass through a system that scales the signal by 2, right? Let's say multiply by 2, so that you get 2 times xn, followed by a square operation, right, which is nonlinear, to get yn equal to 4xn squared. Okay. Now, suppose you switch the position of these two systems, right? Suppose you first take the square. This will give you xn squared, and then scale it by 2 times, which will give you yn equal to 2 times xn squared. Okay, so notice that these two are not equal. So, discussing these properties, these basic properties of the, convolution operator, you get to understand some, implications in the system architecture. Okay. Now, next, what we want to do is to go through several properties of systems that we talked about before. Okay. Now, previously, we introduced some common, properties that we may observe in different systems, such as, systems with or without memory, the invertibility, the causality, the stability, and things like that, right? But previously, we defined these properties in terms of their input and output relation. Okay. Now, for linear time-invariant systems, you can completely characterize the system using its unit impulse response. So what this means is that each one of these system properties that we introduced can be characterized in terms of properties of the impulse response as well. Okay? So each one of these properties implies a certain, condition or a certain property of the impulse response. Right. So starting out with systems that are memoryless, right? So recall that a system is memoryless if its output at any time depends only on the input at that time. Okay. So what this means is that, by the convolutional sum, we know that yn should be equal to summation xk h of n minus k, k from minus infinity to infinity. Okay. Now, for a memoryless system, yn can only depend on the term k equal to n. Okay. So this means that this is equal to xn h0. Okay. So this means that the impulse response can only have a non-zero value at time 0 and should be 0 everywhere else. Okay. So this implies that the impulse response hn should be equal to some constant times a delta function, okay, for some k. Right? So similarly, a continuous time system is memoryless if its impulse response is equal to k times the unit impulse in continuous time, right? Again, for some k. Okay, so if you are given a impulse response with only a single non-zero value at time 0, then you know that this is it is the impulse response to a memoryless system. Okay. Now, in particular, if k is equal to 1, then Hn is equal to delta n, okay, or h of t is equal to delta t. Okay. So in this case, if you compute, let's say, xn convolving with delta n, right? So if you take the input signal x and plug it into this system with impulse response delta n, then, right, this is, summation xk delta n minus k. So by properties of this delta function, this gives you only the value at time x equal to n. Okay. So this means that if you have an impulse response equal to delta n, right, passing any signal through this system will give you an output that is equal to the input. Okay. So this means that this is the impulse response to an identity system. So you can show this similarly for continuous time as well, right? If you take a continuous time signal, pass it through a system with impulse response delta of t, right? You get the integral of x of tau, delta of t minus tau, which is x of t, right? So this shows that the output is equal to the input. Okay. Right. So let me go through one more property. Right. So this is the invertibility of LTI systems. Now recall that a system is invertible only if there exists an inverse system such that when you cascade this system with its inverse system, you effectively get an identity system, right? So suppose that you have a system with impulse response h of t, right? Suppose you input x of t into this system, and you cascade it with its inverse system. Let's call it h1. Then the output should be, equal to its input, right? So this is the inverse system. So when you cascade a system with its inverse system, you get an effective system that is equal to the identity system. So for an identity system, we just showed its impulse response must be equal to this delta function. I'm sorry, we're looking at continuous time here. Okay, so identity system has impulse response delta t. Now the impulse response of the overall system is equal to the convolution of the cascaded the impulse response of the cascaded subsystems. So this is saying that the system h of t is invertible if you can find another impulse response h1 of t such that when you convolve h of t with h1 of t, it should be equal to an identity I'm sorry, it should be equal to a delta function, which is the impulse response of an identity system. Okay, and similarly for the discrete case as well. Okay. All right, so I guess I should stop here, going a little bit over time. So, do you have any questions? 所以你可以了解说为什么 h of t 跟 h sub 1 of t convolve 之后应该要等于 delta of t 吗？
就是因为那个 xt 要再变回原本的 xt。
对，那 OK， 所以你了解说这个就是你如果 cascade 两个 subsystem， 你要去找它等效的这个 impulse response 的话，你要怎么样去做吗？
就是直接把那两个 convolution 起来嘛。
对，你要找它等效的这个 impulse response 你就是取它 cascade 的这个两个 subsystem 的 impulse response 去做 convolution 就可以得到。所以我们就是希望这个等效的 subsystem 是一个 identity system 的 impulse response， 所以这两个的 convolution 就要等于这个 delta of t 这样。OK， 好，那有没有其他的问题？那如果没有的话，我们今天就上到这边。那我们接下去下一个礼拜还有一些其他的 property 像这 stability、causality 我们都希望去 show 说there is a corresponding property of the impulse response that specifies these particular system properties. Okay. Right, so there is a homework one posted on the website, mostly with problems from the textbook. Okay, so please go check it out, and it is due next Friday. Okay, so I think the most important part about this chapter is that you should know that you can characterize any linear time-invariant system using its impulse response. Okay, so we're trying to construct this concept, right? So once you are able to do so, then you can characterize systems or deal with systems using solely their impulse response, okay, instead of having to deal with the complex input and output relation. 好，我们今天就上到这边谢谢大家，谢谢。